Hi everyone, my name is Asha, and today our group will be presenting our OpenTable database design project. For this project, we reverse engineered key workflows from OpenTable and use them to design a transactional database model. I'll be covering the first part of the presentation, including the project overview, the application background, the scope we selected, and our initial requirements. So for our project, we chose OpenTable because it's a well-known platform with clear transactional workflows around restaurant reservations. We started by analyzing how the reservation process works from both the user and the restaurant perspective. From there, we focused our design on the core reservation workflow, and then we developed conceptual, logical, and physical database models. Finally, we demonstrated key functionality through SQL queries to show how the database supports the requirements that we identified. This process looks very linear, but it was essentially a process of fine-tuning as we went along. And the demonstration at the end shows that it was all a process that was worth it. So, OpenTable is an online restaurant reservation platform that allows users to search for restaurants and make reservations. Users can search by location and cuisine, and in practice, they can also use filters like date, time, and party size to find available options. On the restaurant side, the platform helps manage reservation availability and scheduling. They make sure that a party of 15 doesn't book a reservation when there's only room for two. From a database perspective, this makes OpenTable a strong example of transactional system because it depends on accurate connected data for users, restaurants, locations for each restaurant, time slots for locations for each restaurant, reservations themselves, and reporting. For our project scope, we intentionally narrowed the scope to OpenTable's core transactional features. The included features in our design were user accounts, restaurant browsing, reservation time slots, reservation booking and cancellation, capacity management, reservation status history, and business reporting. We excluded features like reviews, the reward system they offer, and table level seating optimization. We made that decision so we could focus on the most important reservation related workflows and build a database that was realistic but still manageable for the project. To develop our initial requirements, we used our prior experience with OpenTable, but we also spent additional time on the platform interacting more closely to understand what users need and what a restaurant would need from this database. So, from the user side, the main requirements that we identified were the ability to search restaurants by city or cuisine, to view restaurant details, to check reservation availability, and create or cancel reservations. From the restaurant and system side, the key requirements were defining time slots by location for each restaurant, setting capacity for each time slot, tracking reservation activity, and supporting reporting by restaurant. These initial requirements were intentionally broad, and we later fine-tuned them in our final requirements matrix and database design. So next, we'll move on to the database itself and demonstrations. Keanu will walk you through our models and implementation, and Andrew will walk you through our database demonstrations. Thanks.
Thank you, Asha. Now I'm going to walk us through our conceptual model. This is going to help show the high-level structure of the system and also show our key entities that we used. The main entities we identified are user, restaurant location, time slot, reservation, and reservation status history. So if we start with the user identity, this represents the diners who interact with the platform. Each user has attributes like name, email, phone number, and the date that their account was created. For restaurant entity, this stores information about each restaurant, such as the restaurant name, cuisine type, phone number, and the price range. Since many restaurants have multiple locations, we separated location information into the restaurant location entity. This helps to allow one restaurant to have multiple physical locations, each with its own address, city, state, and zip code. The time slot entity represents the reservation availability windows. Each location can have multiple time slots per day, and each time slot includes a start time, end time, and maximum capacity. Finally, we have the reservation entity, which connects users with specific time slots when they book a reservation. A reservation stores information like the party size, reservation status, timestamps, and when it was created or updated. We decided to also add the reservation status history entity, which tracks changes to reservation status over time. This allows the system to record when reservations are modified, canceled, or completed. Overall, this conceptual model helps to show the main components of the OpenTable reservation workflow and how they interact with each other. Next up, we're going to go over the logical database model. In this model, each entity from the conceptual diagram becomes a table in the database. The tables include user, restaurant, restaurant location, time slot, reservation, and reservation status history. Each table contains attributes that represent the fields stored in the database. For example, we'll start at the top. The user table stores the user ID, first name, last name, email, phone number, and the account creation timestamp. The restaurant table stores restaurant details like the name, cuisine type, price range, and contact information. The restaurant location table stored address information, and includes a foreign key linking it back to the restaurant table. This allows a restaurant to have multiple locations. The time slot table stores reservation availability windows for each location, including the start and end times and the maximum capacity allowed during the time slot. The reservation table records each booking made by the users, including the party size, reservation status, and timestamps. And then finally, at the bottom, the reservation status history table records any status changes, allowing the system to track how reservations evolve over time. The logical model helps to ensure the data is structured, normalized, and connected through the primary and foreign key relationships. Next, we're going to go into the database implementation. This slide helps to show examples like the create table statements. During implementation, we added several important database constraints. First, we defined primary keys for each table to uniquely identify every record. For example, each user has a unique user ID, and each reservation has a reservation ID. Second, we added foreign key relationships to enforce connections between tables. For example, reservations reference both a user ID and a time slot ID. We also included a check constraint, such as ensuring that each party size must be greater than 0. Finally, we added a default timestamp so that fields like created at and upload at are automatically populated when a reservation is created or modified. These constraints help to maintain data integrity and ensure the database behaves correctly during transactions. The next slide is just a continuation of the last, and this helps to show additional table implementations, including reservation and reservation status history tables. The reservation table stores the core reservation data, including the user making the reservation, the selected time slot, the party size, and the reservation status. We also recorded timestamps to track when reservations are created and updated, and the reservation status history table provides an audit trail for reservation status changes. This allows the system to track events such as when a reservation is modified or canceled. Together, these tables support the main transactional processes of the OpenTable platform, including reservation creation, updates, and historical tracking. With the database fully implemented, we were then able to run SQL queries to demonstrate the system's functionality, which we're going to have Andrew demonstrate next.
Thank you, Keanu, for explaining those models and the database implementation code. Next, I'll be walking us through the database functionality. So to highlight some demonstrated features, I'll show you some example code, but we wanted to show that the users are able to create new accounts. Restaurants are able to input their information for that, so users can browse and see sort of what restaurants are within their area or specific area that they're planning on visiting. And then the reservation booking, modification, and cancellation and reporting. So reservations can be booked by users, it can be modified by users, and they can change the party size as long as it is within the party size limit of what the restaurant can set. They can cancel the reservation, and then the reservation reporting, which restaurants can pull all their reservations for a given day to show sort of what to expect. So example code. So I have the user account creation. This is that information that the user must input except for the user ID, as that's just a unique ID that will the database will automatically input. So this is an example output of what we would expect to see for a user if we were to pull a list of users. Second, here we have the restaurant details and their location. So we have the restaurant ID, which is unique to each restaurant, their name, cuisine type, price range, and their city and state. So let me switch over here to the portal and kind of show you some live examples. So this is the same example. It's just going to show you, I've inserted this information here, but if it would just be the same as if a user were to create an account. And I did the select statement here from the user tables to pull out this information. And with the email has to be unique. So we can't use, user cannot use the same email to create two accounts. In the second example here, we have the two different tables, the restaurant table and then the restaurant location table. The restaurant location table is dependent. There's a foreign key to reference this restaurant here so that they're able to link together and create information for a specific restaurant. Here, I've selected the ID, the name, cuisine type, price range, city, and state, and this is the output down below. Users can, filter by the specific cuisine type, their city, price range that they're looking for in the app. All right, going back here. The next example I kind of want to show you is more of just a walk screenshot example. This gives the restaurant the ability to look at their reservations on a specific date. So as you can see, we have the reservation ID from the reservation table, the user's first and last name from the user's table, the party size from the reservation, as well as its status and its start time from the time slot table. You can go down here at the bottom. It shows the first reservation ID is myself, but it looks like the status of that was canceled. And then you go to the next two lines is myself again, but we have two book statuses with a party size of 4 and a start time of the reservation. Some key features. We tried our best to create a normalized relational schema to avoid any redundant data, to eliminate any sort of anomalies that we expect to find, and just making sure that our data is consistent. And then we have the capacity control time slots. Like I talked about before, the restaurant is able to set the party size limit and then your reservation status tracking, which we saw in the last slide of whether the reservation was canceled or booked, and then reservation history auditing, which we also showed, which is just a list of all the reservations, and then they can filter to active, cancel, and stuff like that, and multi-location restaurant support, which means a restaurant can be in multiple locations, or we support restaurants from all different locations. Yeah, to wrap things up, that's the database functionality and sort of how we expect the reservation workflow to work if they were to use a transactional data type. It gives the ability for users to kind of discover restaurants in their area or specific area that they expect to be visiting. Gives the user and restaurant reservation management kind of list all their things and give them the reporting, and then the capacity control for restaurants to set limits to their party size. Yeah, thanks so much for watching. Hope you guys enjoyed.